Hi everyone. It's a pleasure for me to speak about real-time digital hologram rendering at 20,000 frames per second for ophthalmology in the particular context of Doppler imaging and optical coherence tomography. Okay, let me start with the instrument itself that you can see here on the left. It's actually extremely simple, and it consists of laser light that will shine through an eyepiece, the eye of a patient. The laser light that is backscattered from the eye of a patient goes and illuminates a set of two cameras. One of them is extremely fast, more than 60,000 frames per second, and another one has a lower frame rate, but has the benefit of being able to record all that data up to 10 gigabytes per second in real time, and so we can compute our holograms in real time. Okay, and both cameras see the same interference pattern that is made from the light that is backscattered from the retina of the patient beating against a separate reference in a Mach-Zehnder interferometer system. And from the recording of this interferogram, we compute digital holograms from which we can compute afterwards Doppler holograms, for instance. I will mainly speak about that right here. Okay, let me divide in two very simple steps the process that we do from the interferograms in order to get our images. So first, we do a wave propagation, hologram rendering, basically either Fresnel transformation or propagation of the angular spectrum of the hologram. And then in a second step, what we do is to select a bunch of images, 512, and we compute the temporal fluctuations, either by Fourier transform or principal component analysis. And those images, then, power Doppler, will reveal something very interesting for ophthalmologists, which is the pulse wave in the retinal arteries and some signal in the retinal veins as well. And what is very important is that we can do that in pretty much all the patients that we've been able to image this on in the neighborhood of the optic nerve head, which is about the images that you see are about 2 to 3 millimeters, okay, in field of view. And that used to be a limitation. And the reason for this limitation is the optical safety limit that we cannot go beyond, because we needed to focus the light right in front of the eye of the patient. And this is kind of dangerous because the optical power can become very high in a very limited surface because of laser light. So we avoided this issue by introducing a diffuser, a light diffuser, that makes the instrument now completely compliant with American and European safety standards by simply spreading at the focal point, at the focal plane of the eyepiece, the set of two lenses that make the image, in front of the cornea of the patient, spreads the energy, and then we don't have any problems with the compliance with safety norms. And that's also something that we can do. We can make the eye of the patient, we can move it closer to the eyepiece in order to increase the field of view and get those beautiful wide field functional images of the eye fundus of our patients that will mix the signal in the retina and the signal from the choroid. Let me introduce you to another experiment that we can do. It's the measurement in glaucoma patients. Okay, and here you see on the left a patient with an intraocular pressure of 38 millimeters of mercury, with a very, very deeply modulated pulse wave in the retinal arteries. And this patient undergoes a surgical procedure, a needling procedure, that makes the intraocular pressure drop. And what you can see on the signal, Doppler signal on the right, the power Doppler signal on the right, is that the modulation depth is less important, and the signal is present throughout the cardiac cycle. That is very important because what we now want to do with those Doppler signals, power Dopplers, is a quantitative assessment of local retinal blood flow, ultimately. And for that, we've recently introduced a model that would explain what we see. So basically, we shine the retina of our patients, and then the light is scattered within the deep retina down to the choroid, and then it is backscattered, part of it is backscattered, and we collect the light in transmission from a secondary source of Doppler broadened diffuse illumination. Okay? And whether there is the presence of an in-plane retinal vessel or not, you will get an additional or not Doppler broadening, local Doppler broadening, basically. And you can link this additional broadening in the presence of in-plane retinal vessels, which are mainly transparent, to the local velocity of blood flow. So that's extremely simple, but that would turn these power Doppler signals into maps of the local velocity, at least in the retina. And so here you have the velocity in retinal in-plane vessels through Doppler imaging. Okay. Now let's move on to the topic, the real topic of the presentation, which is real-time Doppler imaging of the posterior segment, which is the retina, with a streaming camera. Here again, you see the instrument with the patient here on the right. And as you can see, we've been able to get the contrasts that we want into the retina of the patient. How did it do that? Well, we used the camera at a frame rate of 20 kilohertz. And we've been designing the system that handles hologram rendering and analysis at a whopping frame rate, a data rate of 10 gigabytes per second. And the way we did that is to basically collect all the data that happens to be there completely asynchronously. The computer cannot know when the frames are coming. So we make a buffer that hosts the arrival of all of our data, and we pick up blocks of data, quite important, like series of images, that we want to transform, to demodulate spatially and temporally in a compute thread. We do that in parallel in the GPU, and then we move back the result that we want, power Doppler image, for instance, into a display buffer, into an output buffer that is used for display or result saving, image saving. And that's it. So the important point is that this enables us to have the kind of contrast that we want. And that's a very good step forward. Speaking of forward, we ask the patient to move backwards in order to do what I'm going to present here, which is imaging of the anterior segment. And we do that at a slightly lower frame rate of 4 kilohertz because there is no not an important broadening as it was the case because of the choroid beneath the retina in the anterior segment of the eye. Let me show you the results that we can get within the iris of patient. I give an example where you see the radial vessels, arteries and veins in the eye of the patient during the opening and the closing of the iris. You can also get interesting results of blood flow through Doppler imaging in the conjunctiva of patients. And ultimately, you can perform holographic OCT. And this is not something that we did ourselves in our facility, but we got interferogram data provided by the team of Maciej Wojtkowski and Egidius Oksorius in Poland. And we used this data into the GPU of our computer and performed the 3D OCT rendering from frames that were acquired at a resolution of 512 by 512 pixels, and the rendering was done at 20 kilohertz, okay? The same as for Doppler imaging. And what you get basically is seen here. Here you are into the depths of the deep choroid. Then you move to the photoreceptors of the retina. And then you can move a little bit more in surface of the retina, and then you see the deep plexus with the macrovascular network of the retina from the deep plexus. Okay, all of that has been made possible by the creation of an open source software foundation that supports the development of high-speed digital holography software for ophthalmology medical applications, but not only. All of that is available at this address. Thank you for your attention.